Okay, hello everyone, welcome to class 25. So, we have been looking at space groups, not so much in detail. I was brushing through a lot of ideas, but important to realize that so it is a combination of point group with Bravais lattices, right. So, with translational symmetry that gives you 73 different space groups. Then we have defined new operations that would not exist in point groups, such as glide and screw, and based by combining this glide screw with the Bravais lattices and the other normal point group operations, we could so the number of space groups just becomes immense, right. So it is 230 different space groups and various crystals. You can actually show that all the crystals actually crystallize in one of these space groups. Now, what is it that so, and then I told you so how to read the international crystals of international tables of on crystallography. So essentially the point of these exercises is to tell you that, okay, so with symmetry, right. So I have prepared the complete template required now to put the atoms, right. So given first the lattice translation, that is how the unit cells are defined, right. So the unit cells and their centering, that is the that's the first part of the space group. It tells me whether it is P, F, or I centered lattice, which crystal system it is, right. So the first part of the phase group space group, which is P, or the Bravais lattice centering I or F or A or B or C, that tells me so something about the template created with respect to lattice translation, or with respect to, let us put it this way, not lattice translation but translational symmetry. The rest of the operations, right. So that is not necessarily a point group operation. The rest of the combination of operations tells me the template, right, created with respect to point operations, screw and glide, right. So screw and glide also include some sort of translations, right. So essentially what I am doing by telling you that my space group, by telling the space group, by mentioning the space group, right, and looking at the tables where I exactly know what point has what symmetry and so on and so forth, right. So which point in a unit cell has what sort of symmetry. So I exactly know the template on which I should put my motif and repeat it, right. Right, I should put my atoms rather, not motif really, all the atoms, right. So every individual atom, I know where to put calcium atom in calcium carbonate, and based on the symmetry, or the space group gives me the template. If calcium, I put it at this particular xyz, I have to keep putting the same calcium, so at this particular xyz, that particular xyz, and so on and so forth. If carbon I put at x dash, y dash, z dash, I have a template ready to put the carbon at all the other x dash, y dash, z dashes, right. And so by cross checking that, okay, so this has this symmetry, that has that symmetry, the template is already there, the space group gave me the template, okay. So now I have to identify my atomic positions, which comes from refining my X-ray diffraction data, and I join this atomic positions with the space group that I already have to get the complete understanding of the crystal structure, okay. So that is how I know what my crystal is, right. So it is not just knowing the space group, but I also need to know the atomic positions, where to put the atomic positions, okay. So so then the template plus the atomic positions right. So, that tells me the complete information about the crystal structure. Yeah, but this template is not just, so when we were doing lattice, right. So, we said lattice is a template on which you put motif and then that becomes, but this template is, so even more coarse grained, even more fine grained than just saying that there is lattice. So, this template includes the lattice, it includes the lattice centering, it also includes, all the symmetry operations about various points which are not necessarily just the lattice points, right. So, that is the template that I am defining. It is a more well defined template, and then I am going to say, okay, so this is where I put the atoms with respect to these template positions, and then I repeat it as the template tells me to repeat, right. So, then I get the complete information about the entire crystal structure. Okay. So, that is so if I open Vesta, let me do that right now. And put in a certain structure, let us say let me open silicon, right. So, if I look at what is the data that I have put in, so one thing is, something about the unit cell. I first told that silicon is in FD 3 bar M space group, right. So, then okay, so that tells me what the template is. Now, I have to, it tells me the structure of the template. Now, I have to actually fix the template. So, for fixing the template, I need to know the lattice parameters, right. So, then I know what the unit cell is and how exactly, if I have some atom in this unit cell, where all should it repeat, but I do not exactly know the size of the unit cell, right. So, first I have to fix the size of the unit cell. And it is enough for a cubic system to know only one lattice parameter, which is A, right. So, that is 5.4. So, in silicon, that is 5.443 in silicon. Then I say that, okay, so what am I going to do then? So, I have to now place the atoms, right. So, the template is given by space group. Where am I placing the atoms? The atoms are, I give the x, y, z positions for atoms. For silicon, it is quite easy. I just put x, y, z at 0, 0, 0, right. Wherever there is origin, I put x, y, z there, right. But then the symmetry repeats it everywhere else. There is a silicon at 1/4, 1/4, 1/4 in this structure, right. So, if you look carefully, you see, so there is silicon at 0, 0, 0, but so this is a silicon tetrahedron, right. So, all this is so this one, for example, is silicon tetrahedron. So, this position hence becomes 1/4, 1/4, 1/4, right. The 1/4, 1/4, 1/4 I do not need to give, right. So, the 1/4, 1/4, 1/4 is generated by just symmetry of the crystal, right. So, unit cell, I go to structural parameters, I just say silicon is at 0, 0, 0, but by virtue of this crystal having an FD 3 bar M symmetry, the 1/4, 1/4, 1/4 is automatically generated. That is what my template says. If there is a silicon at 0, 0, 0, there should be a silicon at 1/4, 1/4, 1/4. Okay. So, that is generated. Okay. So, yeah, so then I know complete information about my crystal. I can actually download it like this, and then I can visualize it. Okay, so that's so this is enough information to know about the crystal. Okay, all right. So sorry, let's go back to so this space group of interest is FD 3 bar M, which is this. The space group that provides the template for silicon atoms to crystallize, or carbon atoms to crystallize in diamond, or germanium atoms to crystallize in the form of a germanium crystal. So, in general, so all these things are actually called diamond cubic structures. You may hear people using the term diamond cubic lattice. Does not make any sense, because the lattice is just so defined by the Bravais lattice, right. So, it is an FCC lattice, but the structure, the crystal structure is what is a diamond cubic structure. It is not the lattice. Okay. So, that is a wrong use of words. Okay. Now, if I look at the number of symmetry operations in diamond cubic structure, or FD 3 bar M symmetry, the template that is generated by FD 3 bar M symmetry, there are about 196, if I remember it correctly, right. So, it is not a few symmetry operations. So, I have to keep a track of all the 196 symmetry operations, right. So, the more symmetric you get, the more are the number of symmetry operations you have. Okay. All right. So all right, so that's okay. So then, so I go from Wyckoff symbol A, B, C, D, E, F, G, H, and so on and so forth. The I, for example, I Wyckoff symbol has much less symmetry than A Wyckoff symbol. The highest symmetry I can find in the silicon crystal about any point is minus 43 m or 4 bar 3 m. Okay, and that 4 bar 3 m is about the origin, right? So I'll look at or half position, which is the body center, and so on and so forth, or 1/4, 3/4, 1/4, and all these positions, right? Is there inversion symmetry in this crystal? Yes, indeed, there is inversion symmetry. But inversion symmetry, so let us actually look at where the 4 bar 3 m is, right? So 4 bar 3 m. So you can see that all these are tetrahedra, and so about any point here, right? So let's take this point, right? So about this point there is a 4 bar 3 m symmetry, right? So that's my origin essentially. Okay, so 4 bar is 2 tetrahedra which are so silicon is this structure essentially. Let me just write it here. So what is the structure of silicon? It's a bunch of tetrahedra, but I have silicon, 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 and silicon, right? So silicon is so silicon is surrounded by tetrahedra of silicon, right? So silicon is at the center of sitting. This is the tetrahedron, right? And the center of the tetrahedron is also a silicon atom, and this atom, right? So this position is my origin. I'm going to take this as 0, 0, 0, and about that point, right? So that point has a 4 bar axis of symmetry that we know, right? So because I have 2 silicons behind, those are these 2 silicons, and 2 silicons in front, those are these 2 silicons, right? So these are 2 silicons in front, these are 2 silicons in the back, and in the center is one more silicon, right? So that's so between these 2 lines, right? So somewhere here is the other silicon, and that is my 4 bar 3 m point. Okay, so I have a 4 bar 3 m symmetry about that point. Okay, however, so if I look at so I mean that point is equivalent to all the other silicon positions also, right? So about any silicon position I have a 4 bar 3 m symmetry, right? That's how I'm going to look at this. Okay, so that's one thing. Now if I look at this, so what is this bond, right? So a silicon is connected to another silicon. This is the nearest neighbor bond. If this silicon is 0, 0, 0, right? So if so the tetrahedra works out in such a way that sorry, I keep on opening this. If this silicon, right, so is 0, 0, 0, then this silicon will be something like 1/4, 1/4, 1/4. Okay. Now it turns out that if I take half of that, right, so I have silicon silicon bond, and I look at the position which is at half the silicon silicon bond, that has a 3 bar m symmetry. Okay, so or in other words, right, so this is the point, or the point is 1/8, 1/8, 1/8. This is 0, 0, 0, this is 1/4, 1/4, 1/4, right. So from the Wyckoff positions, you see, I know that point C and point D, which are like 1/8, 1/8, 1/8, these sort of positions, right. So that has a minus 3 m, or 3 bar m. 3 bar m also has an inversion in it, right. So 3 bar so 3 bar m contains is a centrosymmetric point group, right. So that this point group exists about D and C means that these positions also have centrosymmetry about them, right. So what is the position of centrosymmetry in silicon? So the position of centrosymmetry is between the 2 bonds, right. So halfway point between the 2 bonds. For example, between these 2 bonds, if that position is the position of centrosymmetry. Okay. So if I just consolidate, right, so I have, let's say, 2 silicons, right. This has an inversion symmetry 1 bar, or in fact it has 3 bar m, more than an inversion symmetry. This point has a 4 bar 3 m symmetry. Okay? Okay, good. So, that is how silicon is, right. So, now I ask you the question, what is the space group of silicon, right. So, the space group of silicon we said is FD 3 bar m, right. So, the underlying point group is M 3 bar m. Okay. Now, M means I have 4 by m, 3 bar, 2 by m. Okay. However, you can see in my silicon structure, so this point has the highest symmetry, which is 4 bar 3 m. This has the next highest symmetry, right. So, this is 0 0 0, let us say this is 1/8 1/8 1/8, right. But you can actually see that there is no point in the silicon crystal that has an M 3 bar m symmetry. Okay. The underlying point group is M 3 bar m, but I cannot find any single point in the silicon structure that has an M 3 bar m symmetry, right. So, so none of these points, right. So, I can actually see that easily from the tables itself. The highest symmetry is just 4 bar 3 m. There is no M 3 bar m. M 3 bar m is even higher symmetry than 4 bar 3 m, right. So, that is what we have seen earlier. M 3 bar m is the holohedral point group of the cubic system. However, there is no single point about which there is a point group operation which is M 3 bar m, right. What we have rather is we have a point group operation which is 4 3 bar m, and we have a point group operation which is 3 bar m. These are about 2 different points. Okay. So, there is no single point about which I have an M 3 bar m operation. Okay. Okay. Now, that is something to keep in mind, right. Now, that is what the glide plane does, right. So, essentially if I look at a crystal which is not silicon, let me download that. So, let me go to crystallography open database. Maybe you can also see how I am downloading these structures. Sorry. Or let me state a fact for you, and probably in the interest of time, and you can actually do it yourself, right. So, I am not showing you the platinum structure, let us say, but if I take a structure which is which has a symmetry not FD 3 bar m, rather FM 3 bar m. This is my FCC platinum, FCC gold, right, these sort of structures. Then my 0 0 0 will be a point about which I have an M 3 bar m symmetry, right. In these simomorphic space groups, I have a point right, which has the highest point group operation, right. So, highest symmetry exists, right. So, a point about which a highest point group symmetry that exists in the crystal, right. So, 0 0 0 exists in the crystal, right, and the underlying point group is also M 3 bar m, whereas in FD 3 bar m, right, there is no point in the crystal about which with a point group of M 3 bar m. This is despite the fact that the underlying point group is still M 3 bar m. Okay. But you cannot find a physical point about which the symmetry is M 3 bar m. Now, it turns out that FD 3 bar m, even though it does not have a point about which the point group is M 3 bar m, it acts properties wise, right, it acts like a crystal that has a point with point group M 3 bar m. Okay. So, it is actually conspiring to show greater symmetry than what each individual point has, right. So, the maximum symmetry that a point has here is 4 bar 3 m, right. Now, 4 bar 3 m and then so there is also 3 bar m, right. So, this is about 0 0 0, this is about 1/8 1/8 1/8, right. So, this is actually what my glide plane does, right. So, the so what so what then this does is because I have a glide operation, right. So, the glide operation makes the crystal, although individual points do not have the symmetry of m 3 bar m, right. So, individual points do not have, the glide operation conspires to make the crystal behave as if it has a higher symmetry, point group symmetry than every individual point in the crystal. High symmetry point in the crystal. As a result, if I am looking at properties, right, property wise, so if there is a property that does not exist in platinum, which has an Fm 3 bar m, property wise Fd 3 bar m and Fm 3 bar m should have similar tensors, right. So, for example, if m 3 bar m has a tensor which is sigma 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 0 0 0 0 0 0, then Fm 3 bar m, Fd 3 bar m also should be nothing different, it should exactly have a similar tensor, right. So, all the zeros should actually go to 0. So, if a property does not exist in Fm 3 bar m, it also does not exist in Fd 3 bar m, there is no difference, because properties emerge, are determined by the underlying point group symmetry. So, in all these non-simomorphic space groups, there does not need to be a point with that symmetry, right, but still all the other points, all the glide operations and screw operations conspire to give you that point, so that higher symmetry point group, and this crystal behaves as if it has that point group, right. So, the underlying point group which is just obtained by removing all translational vectors, all translational operations in the glide or screw operation, okay. So, and so the crystal, the properties of the crystal should follow that symmetry, right. So, they cannot follow so that symmetry, for all practical purposes, that symmetry does exist, right. So, even though there is no point in the crystal which has that symmetry, okay. So, that's an important point, determined by underlying point group symmetry, or follow the symmetry of the underlying point group, let's put it that way, or properties of a crystal which are tensors, right, follow the symmetry of the underlying point group. We will expand on this in later classes. But properties wise, Fm 3 bar m is nothing different from Fd 3 bar m, okay. That there is a glide plane does not matter, the underlying point group is exactly the same, okay. So this is what is called Newman's principle. We will expand upon the Newman's principle from next class onwards when we actually look at the properties, okay. Alright, so that is silicon for you. So, silicon is a bunch of all these tetrahedra. Now, we have identified in bunch of all these tetrahedra that this is a point with 4 bar 3 m symmetry, and so the center between the bond is a point which has inversion symmetry, okay. So, let us keep that in mind. Now, from silicon, and so silicon, so I can just so I have a mirror plane, right. So where is the glide coming from, right? So, I have a diamond glide. So, this four-fold axis, right? So, there is a mirror plane which is perpendicular to the four-fold axis, and so let us say, yeah. So, okay. Yeah. So, let us say this is the four-fold axis, which is so this is the mirror plane, right. I do not know if you can see this. Yeah. So, it is perpendicular to my four-fold axis. So, this plane is a mirror plane. So, this silicon should be reproduced here ideally, but since there is a glide, a diamond glide, it will be reproduced at one of these tetrahedral positions, right. So, all the tetrahedral positions, the 1/4, 1/4, 1/4 are created by a diamond glide. That probably you can actually try to geometrically visualize it yourself, right. So, I am just rushing through here a bit. Okay. So, this is equivalent to having a diamond glide. The tetrahedral positions, or everything is filled by silicon. Okay. All right. So, now I am going to change the structure a bit. Okay. So, instead of having all the atoms to be silicon, right. So, the tetrahedral voids, right. So, here I have a tetrahedron. The center of the tetrahedron is also a silicon, right. So, all these are identical atoms. Now, if I do not make them identical, if I make this silicon, if this is silicon and this is oxygen, well, okay. So, that takes different crystal structures, but let us say this is gallium and this is arsenic, or this is zinc and this is sulfur, right. So, these two are not the same atoms, right. So, what I am doing here is essentially I take so silicon, I have a silicon tetrahedra, Si, 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 Si and Si. Okay. So, then I replace this, right. So, instead of having the tetrahedra and the tetrahedral void, here the corners of the tetrahedron and the tetrahedral void are both silicon or the same atom. Okay. That gives it an F, and then it is crystallizing in FD 3 bar M symmetry. But I replace all the centers with, let us say, a gallium atom, whereas I replace all the other corners with arsenic, let us say, and retain the rest of the structure, right, or gallium or zinc, and this will be, let us say, arsenic or sulfur, right. So, this is the structure of gallium arsenide or zinc sulfide, right. Now, gallium arsenide or zinc sulfide, what am I losing? What symmetry elements am I losing by replacing this with gallium or zinc, right. So, we said, okay, so about this point I have a 4 bar 3m symmetry. So, that point is okay. So, I retain the 4 bar 3m symmetry. Because I am not really sorry, about the origin. So, let's put this as the origin. So, about this point I have 4 bar 3m, and I am not really changing the environment about the origin. So, about the origin I still have 4 bar 3m, right. I am retaining that. Okay. But what am I removing? I am removing the this guy, right. So, this point here is a point of centrosymmetry, or I have a 1 bar symmetry about that point, right. But right now, if I take this point, right, on the other side of this point I have arsenic, on this side of this point I have gallium. So, I have removed the centrosymmetry, right. So, I have retained 4 bar 3m, but what I have instead done is I removed centrosymmetry, sorry, which was otherwise existing between these bond centers, right. So, at 181818, right. So, now my 000 happens to be a gallium atom, and 1/4 1/4 1/4 happens to be an arsenic atom, right. So, about 181818 so I have different atoms on the other side on so if I just cannot invert this atom to so if I move gallium to 1/4 1/4 1/4 that becomes arsenic, right. So I mean that is no longer gallium. So there is no inversion symmetry here, there is no 1 bar symmetry, or in fact there is no 3 bar M symmetry also disappears. Okay. So as a result, we have seen this earlier, right, zinc sulphide or gallium arsenide, right, crystallize in a space group which with the highest point group symmetry just being 4 bar 3m, right. There is no so this is the highest point that we have. I do not have an inversion symmetry which is slightly displaced by glide, right. So I do not have a glide plane here. Okay. So I have reduced the symmetry from FD 3 bar m to F4 bar 3m, right. So I just so the highest symmetry point that is both in point group as well as in space group is 4 bar 3m. Okay. So I can visualize that, I think that we have seen earlier. So I can open, let us say, where is the zinc sulphide, right. So this is zinc sulphide. So instead of this is now zinc and this is sulphur, right. So I can zoom it up. Instead earlier the bond the bond, the zinc to sulphur bond, the center of that bond was an inversion center, but now it is no longer an inversion center. I have removed the inversion symmetry from this crystal. Okay. So as a result, all these so these are what are called zinc blende structures. This kind of so I have all these tetrahedra which are aligned. It's like silicon, except that now the center of the tetrahedron is no longer silicon. The center of the tetrahedron is a zinc atom, and the corners of the tetrahedron are the sulphur atoms, right. So it has come I have removed one symmetry element. I have removed some symmetry elements, in fact, right. So I have removed the 1 bar symmetry, I have removed the 3 bar M symmetry, and so on and so forth. Okay. So then that becomes so it's also a non centrosymmetric structure. So all these should be piezoelectric, by electricity should exist. So this is zinc oxide, right, cubic zinc oxide. This is zinc sulphide, this is what is called zinc blende, right. So these set of structures are what are called zinc blende structures. Zinc blende is the name of the mineral, right. So just like we call the silicon based structures as diamond cubic structures, these are what are called zinc blende structures, named after a mineral. Then we have gallium arsenide, we have what is called cubic boron nitride, right. So all these different materials crystallize in these structures. We have what else? Okay. So for now this is enough. So now the good thing about some of these materials, right. So in this structure so cubic boron nitride has a very high thermal conductivity. Okay. Some of these materials are known for their very high thermal conductivity. Okay. So that is so I removed one symmetry and came down to some of the symmetry elements from FD 3 bar M, and then I came down to an F4 bar 3M, and so this has become the zinc blende structure. So you can actually say that F4 bar 3M is a subgroup of F D 3 bar M. Okay. Okay. So that is how we can interpret these structures. Then so you can actually download structure of strontium titanate, which is a perovskite material, and prove to yourself that the space group here is PM 3 bar M, right. So it is a primitive cell, right. So and then in this primitive cell I am placing strontium, one strontium, one titanium, or even barium titanate in the paraelectric phase that we have seen earlier. One strontium, one titanium, and 3 oxygen atoms, right. So that's your motif in some sense. And so with all the symmetry elements so I should have points about which the highest symmetry is M 3 bar M. but I can go back, look at the crystallographic tables of M3 bar M, and I can identify all the other points about which there are other symmetries. Where is the inversion? Are there more points of inversion symmetry? Are there more points where about which I have threefold axis of symmetry, and so on and so forth. Okay. So, so that's how we visualize some of these structures. Then, so there is another structure called the Woodside structure. So, before actually going into details of the Woodside structure, let me reorient the zinc blende structure in a different orientation. Okay. So, let us say I am going to watch it along the 110 direction, whereas my upward vector will be 1 minus 1 and 1. Okay. So, let me apply this. Aha. So, remember this. Okay. So, if I have a zinc blende structure, right. So, what I typically, if I do a TEM, right. So, if I do a microscopic analysis at transmission electron microscopy, what I end up seeing is this is the zinc atom, this is a sulfur atom, this is a zinc atom, this is a sulfur atom. I see these dumbbells, right. So, of zinc, sulfur, these are just tetrahedral bonds, these are just bonds inside a tetrahedron. But so the way the orientation in which I am seeing, I see them as dumbbells, right. So, this is zinc, sulfur, zinc, sulfur, zinc, sulfur, zinc, sulfur, and so on and so forth. And all these dumbbells are oriented in the same direction, right. So, this is the 111 direction, whereas so what I am looking at is 110, the out of plane is direction is 110, and I see these dumbbells. So, just looking at these dumbbells, for example, I can show you where these dumbbells are. Yeah, here for example, right. So, in one of these domains, right. So, this is a TEM micrograph. This is not zinc sulfide, but this is some sort of cadmium telluride. Cadmium, is slightly, tellurium is slightly bigger than cadmium, or the other way around. I am not sure what are the atomic numbers, but you see some atomic number contrast here. So, if this is cadmium, this is tellurium, this is cadmium, this is tellurium, this is cadmium, this is tellurium. So, you see these dumbbells. So, once you see these dumbbells, you can so this is these are atoms. I am showing you a transmission electron micrography image, right, of all these atoms. So, inside this domain you see these dumbbells, and so I can also identify that this is, let us say, cadmium, this is tellurium, and so on and so forth. So, just looking at these dumbbells, I can I am looking at my zinc blende structure in a certain orientation, typical orientation. So, I can come back and then say that this is actually a zinc blende structure, right. So, this is a zinc blende like structure, okay, or a cubic structure, right. So, a cubic structure has these dumbbells all oriented in the same direction. If you look at the orientation of these dumbbells, this is how I am visualizing this. I am looking at the projection image and I am trying to visualize it in this fashion. But there are so many other things that are happening here, right. So, the dumbbells change. Okay. So, we will look at all the other things that are happening in this image in the next class, when we actually look at what are called Woodside structures, which are very close to zinc blende structures, but they have a hexagonal symmetry. They have a hexagonal crystal structure, whereas zinc blende has a cubic crystal structure. But just looking at atomic arrangements, these are sort of quite close, right. So, we will look at Woodside structures in the upcoming class. Okay. So, with that, let me conclude this by saying that so we have tried to visualize, understand what space groups are. They provide the template, and in this template you have to put atoms to understand your crystal structure. We tried to visualize silicon space group FD3 bar M, and said that the D3 bar M, the diamond glide, actually gives it a higher symmetry than what every individual point has, if we are actually looking at the properties from symmetry. And from there we came down to the zinc blende structure. We have removed, we have replaced one of these silicon bonds with two different atoms, and we said we have removed the centrosymmetry and made a piezoelectric zinc sulfide or piezoelectric gallium arsenide, or so all these different materials that crystallize in the structure. And we are actually trying to play around and see how we visualize it in different orientations. In one of the orientations you should see these dumbbells, and this is what you record in TEM. Actually, it's not a construct. I am actually seeing these atoms inside a TEM, right. So I just wanted to show you that this sort of an imaging is possible at atomic scale, right. So, and then you can visualize and then come back and then understand your structures, right. So you can experimentally prove that what you have is indeed a zinc blende structure. Okay. So with that, let me conclude here, and I will see you in the next class. Thank you very much.